So, good morning, good evening, good night, everybody, and thank you for joining me on the starting lecture regarding our chapter 7 that focuses on dielectric materials. And of course, the course is still the one and the only solid state physics. So, let us first celebrate a little bit for our accomplishments that we have made so far. So, essentially, we have gone all the way through these different chapters, and we are here almost done. So let me remind you that the final chapter, it's more like a recap lecture where we do not focus that much on new concepts regarding solid state physics, but rather we kind of reintroduce the things we have already discussed in slightly new settings, maybe apply them slightly differently in different topics regarding nano-sized materials, so that we can maybe understand better the main concepts. So in a way, this chapter 7, where we focus on dielectric materials, will be our only leftover chapter we will have on this course. And here is the table of contents for the chapter 7. So on here, I felt that maybe it's better than instead of the electronic properties of dielectrics, we will focus then on their optical properties and the calculational tools and the main principles that we should keep in mind when we are thinking of insulators as a class of a material. And at least I feel personally that this sense or focus in our treatment, that this is very logical. So when we are thinking of dielectric materials, as the name suggests, they don't conduct electricity that well due to the fact that they have a quite large band gap, and neither these materials are semiconducting. So from that point of view, if we are thinking of potential applications of such materials, we should look elsewhere and not on the kind of usual electronics related applications. Of course, you can make insulators, capacitors. We are using dielectrics in such components, but let's not focus on them, but instead focus on something else. And at least I really like this, that we are looking during the course into the different properties. Like we were looking into the thermal properties, we're looking into the electronic properties, and also here we're trying to look a little bit on the optical properties. Some students don't like this because I guess maybe they think that it's so obvious that I, as a optical physicist, want to focus also on the optical responses. But I think it's also makes great sense from the point of view of the material class being dielectric. And this hopefully also clarifies a little bit of the kind of the concepts and methodology we're using in semiconductor industry when we are doping materials. So mainly the 7.5 section there at the end of our chapter, we are seeing similar behavior with our solids by adding impurities into a dielectric material matrix. But here, let's get started with our first lecture. You have now been giving a slight motivation for this final chapter and a slight a provision of a bigger picture. So let's now actually go through the kind of main concepts and parts that we will be discussing in this very first lecture. So I will be brief in this first lecture that we are focusing on macroscopic description. And what I will do here is that I will just go through again the basic equations and laws that govern the classical electrodynamics. And of course, you should know that this really mainly means that I will reintroduce to you the Lorentz force and the Maxwell's equations. And incidentally, since in this course we have just went through the Hall effect, Edwin Hall's discovery that was made of the Hall effect in 1879, and that is really a direct consequence of the Maxwell's equations. So essentially the treatise Maxwell published on electrodynamics that was done in 1873, if I have the year right. So Hall's discovery was made only a few years after that. So I think this is a nice piece of historical physics to keep in mind here. So that's how physics progresses. Somebody makes something, and then some people are thinking what this implies in terms of other things. So basically, the Lorentz force that we are now thinking as a separate equation that is not related to the Maxwell's equations, that was originally included in the Maxwell's treatise of 1873. And Lorentz force, of course, is, as we recall, Hall effect and the Hall field. The Lorentz force is a very key ingredient in understanding how come we should have a Hall field in a material that is feeling an external magnetic field, and then subsequently we understand how come people were thinking of making that kind of experiments soon after James Clerk Maxwell published his compilation of equations. And by the way, our vector notation was not in vogue during that time, so Maxwell's equations in the original form, I think they had around 30 equations, so equations for all different Cartesian coordinates separately. So no vectors were used during that time. So that was also one thing that is quite different if you would really look the original paper from Maxwell. But let's get forward with our topic. We have babbled too long already for matters that are not the main focus of this very lecture. So, like I promised, I will just reintroduce to you the macroscopic Maxwell's equations here. And I will be brief because I'm pretty sure that at this stage of your studies, you have already encountered them many times, and you have already, for example, also encountered the microscopic Maxwell's equations, so that you know what we are going to be introducing to you here, or reintroducing to you. And maybe from the point of view of solid state physics, you should always remember the Lorentz force. And Lorentz force, of course, is this equation that we have a force, F, that is being imposed into our charged particle that has a charge, an amount of Q, if it feels an electric field. So F equals QE, plus in case there's an external magnetic field, then the magnetic contribution to this force is Q times the velocity of the charged particle with the cross product of the external magnetic field. So this F is the force that is felt by a particle that is associated with a charge of an amount of Q. E is our electric field, and it may also be a quickly oscillating field, so it does not need to be a static field. And B is our magnetic field. And V is the velocity of our charged particle. So in case the electrostatic approximation applies, so that the charges that we are interested in understanding how they are in our system, if the velocities are small, then the Lorentz force essentially just turns into this F equals QE. And if I remember it correctly, this is also then known as a Coulomb equation or Coulomb force. And this is always, or most of the time in solid state physics, that's the regime where we only need to be. So we don't need to consider the velocities of the charged particles. Of course, the Hall effect is a nice counter example of this, that it's not always that the electrostatic approximation applies. And what this Lorentz force tells to us, well, first of all, it implicitly, maybe not very explicitly, but at least implicitly, defines us what are the fields. So what is electric field and what is the magnetic field? So this is what it also tells to us. So for example, we know how a force, how it behaves, what kind of object it is. In terms, if we would, for example, reverse the flow of time in our system, or we would make an inversion operation on our system. So we would know how a force would change. And this then implies what are the transformation properties of the electric field and the magnetic field. So that's, for example, what's being said here. And we know that a force in the normal, like a time domain and in a spatial domain, is a real valued quantity. So it's not a complex valued field. Then we also know that the time-dependent field E and B, they are real valued fields. And this is, of course, many times a great source of confusion for younger students and maybe for older students too, because most of the time when we are actually using E fields and B fields, and especially in electrodynamics and optics, we have a complex valued fields, and somehow we forget the fact that actually, in fact, the Lorentz force defines the fields as a real valued quantities. So in the end of the day, like when you have a complex valued field, you should always remember to take the real part so that you actually get a real valued field. If you're familiar with Fourier transforms or similar integral transformations, maybe remembering them helps. So when you have a real valued field and then you take a Fourier transform so that you end up with a description of the same mathematical object and physical object, the same field, but now in the frequency domain or in the Fourier domain, in the K-frequency domain, there you may have the field as a complex valued quantity, where the imaginary part, the complexity of your field tells us of some relative phase differences between different frequency components of your field. So not all the field components, not all the sine waves, or plane waves, they need to be in the same phase. So this possible difference between the relative phases then gives rise to the fact that we are actually then dealing with complex valued numbers. So I hope that these things you would be already familiar with them, and if you are not, please discuss with me during the discussion sessions and then the homework calculational sessions, and I will try my best to explain what I'm trying to say here regarding the points of electric fields and magnetic fields and forces of actually being real valued quantities, and how come so many times we end up treating them as complex valued fields. So we have this exponent I omega t there, then meaning that in fact there seems to be some kind of controversy in our mathematical treatment, and in the piece of a physics or piece of a physical reality we are trying to describe with these fields. This is not a simplest of things that we have in physics and regarding field quantities, but this is not that difficult neither, and at least to me it always helps of remembering things through the Lorentz force. So that's also the kind of importance of this equation. So it really also defines how the fields are. And this, for example, the real valued fact of the fields, the necessity that they're real valued, and then also their transformation properties. That how come an electric field is a vector quantity and how come the B field is actually a pseudo-vector quantity. But maybe that's beyond our curriculum on solid-state physics. Well, now we know everything we need to know ever about the E field and B field, and we can now proceed in writing the macroscopic Maxwell's equations. And these were the equations more or less that Maxwell originally formed. So he did not actually use the microscopic Maxwell's equations. They were done later by Lorentz in order to explain how come we have these kind of auxiliary fields in the treatment, and how we could understand Maxwell's equations to originate from the microscopic point of view. But in any case, like, these are the equations that we have, and I hope everybody remembers them already. So we take the divergence of our displacement field D, and that must be equal to the free electric charge density of our system, our material. So this is the first equation, also known as the Gauss law. Then we have the second equation. So if we take the divergence of the magnetic field, this must be equal to 0 at all times, and this is essentially originating from the fact of the properties of the magnetic field. So this is how the E field and B field are being defined, so that this is also resulting equation from that fact. So this is the basic properties of vector fields. In a way, like, normal numbers can be even or odd. Similar kind of properties we may have with vector fields. Then if you take the curl of the electric field, so essentially this is the Maxwell-Faraday equation, this curl must be equal to the minus time the derivative of the magnetic field. And then the same thing in a way for the magnetic field, or to be precise for the magnetizing field H, so that the curl of H must be equal to the free electric current density JF plus the time derivative of the displacement field. So that's the final equation known as the Ampere's circuital law. So the first one is known as the Gauss law. The second one is the Gauss law for magnetism. 3, that's the Maxwell-Faraday equation, and 4 is the Ampere's circuital law. So and these are forming the Maxwell's equations. And as we all know, basically most of them were already known to mankind before Maxwell, but essentially Maxwell was doing a contribution into the Ampere's circuital law, so that he kind of added these terms here, so that they this would form a kind of complete treatment. And the nice thing about Maxwell's equations that you can actually form a wave equation using them, and then we see that we actually have a propagating electromagnetic field as a result of these equations. That's one of the nice things about Maxwell's equations. Another one would be that, for example, they could be used to make beautiful t-shirts with the equations either on your chest, on your back, I don't know, depending on how brave you are in wearing such t-shirts. I would love to get such t-shirt, please. Don't laugh at me, but I would enjoy that. That kind of guy. Rho F, like I already mentioned, that's the free electric charge density. The JF, that's the free electric current density. More on this, what we mean with free later. And then we have these helping fields that are defined in the macroscopic formulation of the Maxwell's equations. So we have the auxiliary field D, which is also known as the electric displacement field. And we have the H field, also known as the magnetizing field. And these are defined, please note, defined in a way that the D field, displacement field, equals to the vacuum permittivity E epsilon naught times the electric field plus material polarization P. So this is the equation that kind of is defined as it is in order to macroscopic Maxwell's equations to work out. And we have a similar helping field that we use to define the Maxwell's equations. So we have this H field, also known as the magnetizing field, and H equals 1 over mu naught, the vacuum permeability, times the magnetic field minus M, where M is the magnetization. So essentially here, they look almost symmetrical. Okay, we have plus sign here, minus sign here, and we have permittivity here and 1 over permeability here. But basically, this is kind of helping fields. And here, the question marks would be, especially from the solid state of physics point of view, is that how we could calculate or how we could estimate what is this source polarization, what is this material polarization we have, that if an external field is being applied, how the displacement field is being affected by the material. And the same thing if we have a magnetic interaction, that how come, for example, the incident B field gets modified due to the presence of the material, compared to the case that we would just have a vacuum in which the B field, the magnetic field, would be propagating. So D is the electric displacement, P is the material polarization, and H is the magnetizing field, and M is the magnetization. So please note, P and M fields would be then usually of our main interest if we are more focused on solid state physics. So we kind of are looking at things from the materials point of view and not the kind of fields as such. So our focus here is not as much on the fields and modifying them, but rather how the material is modifying the fields. And finally, what we will do in this lecture is that we will also connect the macroscopic bound charges. So they are not free charges, but bound charges. So rho B and the bound currents, so JB, to these auxiliary fields. So the material polarization P and the magnetizing field M. And these are defining equations. So we must use these kind of equations in order for the macroscopic Maxwell's equations to be compatible with the microscopic Maxwell's equations. So we define them like this, so that then we can have both of the Maxwell's equations to be compatible, equal. So the bound charges are being defined that they are basically the minus of divergence of the polarizing field, the material polarization. And then the bound currents, so kind of currents that are being formed inside the material, but they are bound, so they are not like free, so not really like a macroscopic currents propagating in the material, but rather very tiny nano-sized currents. And they are being defined that they are the curl of the magnetizing field. So that's the first term, and then plus the time derivative of the material polarization. And now all these equations we have reintroduced to you, they can be used to essentially describe the light-matter interaction in full on the macroscopic scale and when we are treating things classically. So we are not interested in single photons interacting with single atoms and so forth, so that we don't need to resort into the quantum mechanical treatment of fields being quantized and materials being quantized. But most of the time, like, we can treat things classically, and then thus most of the time we are perfectly fine in just describing all possible light-matter interactions with these equations we have just shown to you. And the problem we have here, and this will be the kind of main focus in this chapter, is that we need to kind of understand how we could link the microscopic picture of a solid state of matter to these polarization field P's and the magnetization field M's. So this is our interest, kind of main focus on this chapter that we are having now. So how we could describe how P and M could be calculated if we would know, for example, what are the kind of microscopic atom scale responses of materials, of solids. So if you know how the solid looks like, what kind of atoms it is made out of, and we would know the lattice, how the crystal is being formed, we could somehow calculate what would be the subsequent material polarization P and the possible magnetization M for this substance, this piece of solid. So this is our problem statement that we want to unravel in the upcoming lectures. So this was the first lecture. I thank you for your patience, and I wish you a pleasant night or day or evening, and please hurry with me to the next lectures. We will be kind of continuing in solving this problem we have just outlined to us. So thank you, and bye-bye.